we're going to be looking at conformational analysis. Do you guys remember what conformational isomers are? We talked about it probably really briefly during the first or second day of class. You guys remember every last little detail that I say to you guys, right? So conformational isomers were isomers that differed by a bond rotation. So essentially what we're doing here is we're going to be looking at the energy changes with bond rotations. So this is, energy changes with bond rotation. Okay, so I did show you guys a little bit last time the way these drawings are going to work out. But today I brought some models to work with, to play with a little bit, just to illustrate a little bit more what exactly we're looking at. And let me zoom this camera up a little bit, because I'm going to have the model underneath the camera the whole class period just about. All right, there. We straighten this out. And there we go. Okay, so essentially what we're going to be doing in a conformational analysis is we're going to look at it from, we initially look at it from this perspective. This is how we draw it on paper, the zigzag lines. And we're going to be looking at it like, say, down this bond right here. So the perspective is straight down that bond, such that when you have them lined up, you basically can't see that bond anymore because they're behind each other. So essentially we're going to be looking at it from that perspective. And we have to be able to draw these. You want to get to the point with the stuff where we don't need the model kit anymore. You can just do this stuff without a model kit. And that's going to take a matter of practice, and it may require the use of a model kit. So remember, we talked about it last time, we do have access to these model kits in the Resource Center, the Tutoring Commons, they should have them there, and we also have them in the lab. And you come ask me, I have a ton of these models in my office, actually. I have a whole big drawer full of this crap. So if you guys need to borrow anything, just let me know, I can let you borrow them. Just make sure you get them back to me if you borrow anything from me. All right, so basically what we're going to be doing again here is we're going to look down a bond and draw what we see. There are infinitely many possible conformational isomers, because every time you change the bond angle by anything greater than 0, just changing it just a little smidget is actually enough to be a new isomer. But we only look at particular angles where we're looking at 60-degree bond angles differ from each other. And we're going to label all those. So before we do that, I want to just draw on paper here exactly what we're doing, just to make sure everybody's on the same page here. So that. So once again, I'm going to make this line up with my paper. It's typically what you're going to do is kind of line it up with your paper. Okay, that's the zigzag that's in the plane of the paper, the black carbons. And then the dashes and wedges are the white groups here and the white and yellow group over here. And we are going to be looking at it from the perspective where we're looking straight down this bond. So see how good you guys are drawing a little eyeball. You don't have to draw little eyes here, but I'm just showing it. This is the perspective, the little eyelashes in there so you know it's an eye. And that way. All right, so looking at it from this perspective right here. So this is what we see. Let me put it right underneath the camera. Okay, and we're basically going to represent the back carbon and the front carbon. And the way we do this is the front carbon is a dot. So this is going to be the front. And for this particular, just to illustrate what we're doing here, I'm just going to draw them separate. We are going to be actually watching or drawing them overlapped. So we have the front carbon as a dot. The back carbon is a circle. And then you just draw the groups that are coming off of it. So the front carbon, so we're looking at it basically this carbon and this carbon. So there's your dot, there's your circle. And the front carbon, we see that there is something going upward. And then we see groups coming down left and right if we're looking at it from this perspective. So we're looking at just the front carbon here. And then the back carbon, looks like there's a group going downward. So down, and then up, up. All right. So the way we actually draw these is overlap. So I like to draw the circle first, put the dot in the middle. So then we have the front carbon there, and then the back carbon. It's actually similar to the reason why we do these drawings. We're basically trying to represent three-dimensional objects on a two-dimensional space. So we have to do some kind of convention here to convey 3D. Okay. Are there any questions about this so far? Okay. So I want to go ahead and label a few groups here, just so we can see what the bond angles are. There are a couple angles that are important. So let's say from green to green, and then let's put, I think I'll put a red one over here, just so it's different. And we call the angle between groups on the front carbon to groups on the back carbon. Do you remember what that name was? Phi. That was the Greek letter is phi, but what do we call that angle? It was the dihedral angle. So once again here, the dihedral angle is the angle between a group on the front carbon and a group on the back carbon. So dihedral angle, you're going to use the Greek letter phi. So it's phi. And this is the angle between a front and back group. All right. And it works out where if two groups are directly overlapped, then their bond angle is 0. So if we're going between, like this one, green to red here, that angle, that's a 60-degree angle. And we're not going to be working in radians or anything. We're going to use this degrees. So no radians. And then there, what do you guys think that bond angle is? 180. Yep. Okay. And we had the other possibility here. So in order to get to the 0-degree angle, there actually are no 0-degree angles in here because they're all kind of staggered out by 60 degrees. All these little gaps here. The way that we would get to the situation where they are overlapping, we have to rotate one of the carbons 60 degrees. I'm going to go ahead and rotate the front one. So we're rotating the 60 degrees. They now overlap. And we now have to be able to draw that. So they're overlapping. I rotated the front carbon so it now looks like this. We need to put the drawing that up there, like that. And then the back groups are now overlapped. If we're keeping track of everything, the green one is now over there. It's now right here. The original red one was back behind it now. And then this green one didn't move on the bottom there. Oops. Now this one has a bond angle or dihedral angle of 0 degrees. Okay. In the situation where you have all of these are 60 degrees apart, this conformation is referred to as being staggered. So this is the staggered conformation. And we're going to call this lower energy. What we're doing today, essentially, this conformational analysis is kind of an extension of what VSEPR was. That was the theory that we basically would arrange groups on atoms so they're really far apart from each other. Just now when you're doing with larger molecules, they're happening across a larger space. And this is the way that nature achieves it, is by staggering things or eclipsing them for high energy. So these are eclipsed, and we're saying that these are higher energy relative to each other. Okay. It turns out that each of these possible interactions has an energy associated with it. So in order for you to get a full 360-degree bond rotation, there has to be enough energy in the system to push through all these energy barriers. So every time you have energy associated with these, they have an energy barrier. And the biggest barriers are the eclipse conformations. And if that's the situation where we actually can't push through the eclipse conformation because it's so high energy, we actually can't even get to it. So it effectively acts as a wall for your bond rotations. All right, so once again here, in general, staggered conformations are lower energy, meaning they're more stable, more favored. That's the general trend in this class. Things that are lower energy are favored, and then things that are eclipsed are not favored. Everything that we're going to be doing with these conformational analysis is going to eventually lead to the chair boat conformation that a little joke I had here earlier, the chair and the boat. This is basically an extension of this. It's basically an application of what's happening here. Okay. Are there any questions so far? Okay, so what I want to do now is I want to go ahead and do some bond rotations, and typically we have some energy diagrams that go along with this. And we talk about the energetics of it. Okay, so let's start with the simplest molecule really that we can do this with is ethane. So ethane is what? CH3, CH3. So I want to go ahead and just draw out the carbons, just so we're clear on what's going on here. And I'm going to go ahead and already draw it in the most stable conformation, which is staggered. When you're drawing it in the staggered conformation, and you're looking at the dashed wedge, that's where the dashes of the wedge are kind of pointing in opposite direction from each other. And what you effectively get is that zigzag pattern that we talked about before. And the perspective, so here's our little eyeball. I've been rereading Dune lately, so it's colored eye blue. Like one person's read that book probably in this class. They all have blue eyes in that book, and they're like glowy blue. So, all right, there that way. So I want to go ahead and use this model here, and I'm going to go ahead and when doing these, I recommend having one of them on here that looks different than the others at the reference point. So I did that already. That's why I have this funny yellow one on here. I believe this yellow one's normally for phosphorus. But let's go ahead and match up the conformation. So lining it up with the paper looks like that. The yellow one is still a hydrogen. We just want one to look different. So we're basically going to look at it like this. And what we're going to do is draw this first conformation and then rotate it 60 degrees. And then keep going. And look at the energies with it. And I'm going to label this on paper by just circling the hydrogen that lines up to. So that hydrogen is this one. All right. So I want to go ahead and draw that. So I'm going to go ahead and do this down here. And this will be our starting point. Okay. And that's this hydrogen right there. There we go. Okay, so technically you can rotate any of the front or the back, or rotate them both simultaneously. That technically is correct too. But I recommend that if you're working with the model kit, just rotate the front one. So this one, it's holding it up, so you can just go like this to rotate. You could make it complicated and rotate the back one, but whatever you got to do. On paper, it does not matter. Make your choice which one you want to rotate. So I'm gonna, for the sake of discussion here, we're gonna just go clockwise. You could go counterclockwise also, it doesn't really matter. But we are gonna do a 60-degree bond rotation between each one of these. So what happens now is this is now like that. So essentially what's gonna happen is here, they're gonna alternate between staggered eclipse as we go around. All right, so we now have these eclipse conformation, like that. And then these are now overlapped. These are kind of challenging to draw at the time, and they're overlapped like this. But that is your eclipse conformation. And that hydrogen is now there. All right, I am then going to go ahead and bring it here one more time. And I think for this particular problem, we're just going to do these three. All right, so the H that we're identifying is now like that. So it looks like it's down towards the right now. So it's here, and I want to go ahead and circle it. And then the H is H, H, H. Okay. So if we take a look at the energetics of this, so here we have energy, and then on the x-axis you would have dihedral angle, phi. And what ends up happening is that these are lower energy, the staggered conformations, and it has to go higher for the eclipsed and then comes back down. Don't memorize these numbers. I'm just giving you an illustration of how much energy we're talking about here. This works out to be, for this particular compound, it's 12 kilojoules per mole. 12 kJ per mole. And if you think about the stuff we did like back in general chemistry, most reactions are on the order of hundreds to thousands of kilojoules per mole. This is very small energy in comparison to an actual reaction. So, what do you guys think? What would be the energy for a full 360-degree bond rotation, do you think? So this one was 12 kilojoules per mole. So basically, you have to step through that. How many times are you going to have an eclipse conformation before it's fully turned around? You're going to get that. You're going to get that conformation 3 times. So let me show you. So we have the starting point. There's one eclipse conformation. Here's the next staggered. Next eclipse conformation. Next staggered. Next eclipse conformation. Full bond rotation. So it has to do that 3 times. So it would be, for full bond rotation, would be 36 kilojoules per mole. So full bond rotation is 36 kilojoules per mole. And the reason why is because throughout the bond rotation, we have the eclipse conformation 3 times. So 3 times eclipsed. Okay. Are there questions so far here? Go ahead.
Not with that, but for the actual structure.
What about it?
Like in the book, it had to where it was split like the other way, like for just a regular staggered. It was, you know how you have it down the front card?
So they had it like this versus this.
Yeah.
Like we were actually drawing it from this perspective. It doesn't really matter.
So it doesn't matter.
Does not matter. No.
Okay.
It's just it is the view that you're looking at it from.
Yeah, that's how it was. So
yeah. So basically, what I want you guys to do is your drawing matches this drawing that you did. So whatever drawing you did for this part, it's kind of creepy. And then you go ahead and just make sure it matches. So in this case, I drew this carbon going up. So that means I should start with this up. Where if they had it down, then I would have had it down. I think in the notes from Tuesday, I actually had it downward in those notes. So it doesn't really matter. So go ahead.
So does that mean like if you hit it with 12 kilojoules of energy, it will turn like that?
It could, yeah. Basically, if it only, suppose it only had 12 kilojoules, it wouldn't be able to do a full bond rotation. It wouldn't have enough energy to push to the next one. Because it has to be able to push through an energy barrier. Every time it has to go through an eclipse conformation, there's an energy with it. And since I have to do it 3 times, then it's going to have that energy need to be there 3 times. So 36 total.
So it's not producing that energy?
No, that's how much energy is required.
Okay.
Like energy input. I mentioned this briefly when we went over the IR stuff. So it turns out that we can look at bond vibrations with IR, and then I believe it's Raman spectroscopy is for bond rotations. That's also, it's just another energy type. It's like a little bit outside the range of what IR was at. All right, so the energy of bond rotation is referred to as the torsional barrier or torsional strain. So torsional strain, this is basically the energy barrier of bond rotation. So energy barrier of bond rotation. And if you think about what the word there, torsional torque, you guys know what torque is? That's when you're like turning something. So yeah, same kind of thing here. So instead of torque, we just say torsional strain. All right. So the next molecule I want to look at is I'm going to go ahead and flip these ones back to carbons. Where did I put them? Put them somewhere over here. I do have more carbons to work with, but I didn't want to. There they are. I didn't want to dismantle my structures here. All right. What I'm going to do here now is we're going to go ahead and do the same problem with butane, and we're just going to, instead of this yellow one being a hydrogen, we're going to call it a methyl group instead. So you always want some kind of identifying feature there on your model to help you keep things straight. All right. So what we're going to do, so I want to take a look at a couple different views here, and then we're going to do the whole bond rotation thing again. So here we have butane, like that. So typically, when you're being asked to draw these conformations, the person asking will specify what carbons you're looking at. The ones that are most notable for this particular problem would be looking down C2 to C3. So this is carbon 2 to carbon 3. And you could be asked to also show from carbon, it could say C3 to C2. So whichever one it has first is your front carbon, the one it has second is your back carbon. So we are going to look down this way and going from C2 to C3. And then typically what I like to do is I like to fill in the detail of the two carbons of interest. So I'm only going to fill in the H's for 2 and 3. I'm going to go ahead and leave 1 as just the line there. So this should be coming down like that. And these are going to be H's, right? Okay. Here we go. And once again, that's the eyeball. That's the perspective that we're looking at. So starting off, just line it up with the paper. So remember, we're saying that this yellow one is carbon 1. And that's going to be our identifying feature. And that is what we're going to draw. Oops. All right. So let's go ahead and draw this. So the front carbon, and I want to give myself a bunch of room to put the graph above it. Oops. Camera turned. There we go. All right, so going upward, so having the model right here, have it handy. So let's put it over there. So front carbon has going up, what is that? That is a CH3. So you could put it as CH3 or you put ME for short. Filling in my H's now. And then we have the back CH3. And then what I'm going to go ahead and do is label that one. Actually, I think I'm going to do the graph below it. Looks like I kind of just didn't leave myself enough space there. Okay, and then just like the last example, we're going to go ahead and grab that one. And we're going to turn it this way in 60-degree increments. So that's going to go like this. So it's going to look really similar to the last problem we did, except for now, instead of having H's overlapping, we are going to have a CH3 and an H now overlapping. So CH3, H in the back, down is an H, this way is an H, then back carbon, that on the bottom there has a methyl, and then here we have an H. And labeling things again. that. So doing enough of these, you probably don't need a model kit so much after you've done it just done this a few times. So we're now here. And I'm going to label all the different conformations. I just want to get them laid out here, and then we'll start labeling stuff. So we're turning it that way. Okay, it is now staggered again. Remember, they always alternate between staggered eclipsed, if you're going in 60-degree increments. Okay, got that one. And the group of interest here now is that. Okay. Next one, if we bring this now downward, this. And this is the last conformation I want to show for this one. And then we'll do some different examples. Like that. So now look at them. The methyl groups are now overlapped. Okay. So since we now have some non-H groups on there, we now start recognizing where the large groups on the front and back carbons are relative to each other. It turns out that if you actually fill in some of the bonds on here, let me show you something real quick. So I'm going to go ahead and put on a hydrogen on this one and a hydrogen on this one. These are the large groups on the front and back carbon. When they are eclipsed, they actually, when they are eclipsed to each other, they actually touch. And nature does not like that. They wants to kind of push them away from each other. So this is actually the least preferred conformation, is when they are eclipsed, the large groups overlapping. The most favored conformation is where these large groups are farthest away from each other as possible. That's the one that's favored. So this one actually matches the first one, right? So this one right here is referred to as the, it still is staggered, but specifically it is the anti-conformation. So it's anti, and this one here, large groups. Phi is 180 between them. All right, this one's eclipse. Nothing special, too special about that one here. This next one here, notice how the large groups are kind of coming into a proximity. In this situation where it is staggered, but the large groups are 60 degrees apart, that is the Gouge conformation. So G-A-U-C-H conformation. And bless you. So this one here, the large groups, the phi is 60. So they are just a little bit away from each other. And this one here, this is a special eclipse conformation, but we don't actually have a special name for it. I'm just going to call it the highest energy. And it is eclipsed. And it works out where that's the highest energy one because the largest groups are right overlapping each other. Okay. Are there any questions about this? See, there's a lot of panicking going on.
And in the exam, when you say like, diagrams for the second eclipse, you have to do all the ones in between?
I typically specify things like highest energy or lowest energy.
So you have to show like the mid-two one, which is how you get to the final answer.
Only get to the final answer. Yeah. I typically don't have you guys draw out everything. I will specify things like highest energy, lowest energy. And that's typically what I'll do. I'll give you a structure, and then I'll give you a name, and then tell you which carbons. And then from there, you go ahead and figure out which one's highest, which one's lowest energy.
Also, if we were to say take the front carbon and back carbon and rotate them both together at the same degree to get them pointing upwards, does that matter? Unless they're all.
I think if you're rotating front and back simultaneously, it's easy to lose track of where you are. It's technically not incorrect, but I don't recommend it. Just because you can get lost in where things are turning. So that's your call to make, if you want to do it that way or not. All right, so let's go ahead and take a look at a different example. But first things first, how How many Gauge interactions does this compound go through in a full 360 bond rotation? Those are 2. Yep. It has one this side, and then if it goes around that way, it's going to have another one going this way before it gets to there. And these are still high energy, the eclipse ones, but the highest energy one is the one where the large groups overlap each other. Okay, I want to go ahead and do another example here. This time I'm going to go ahead and add some carbons here. And I want to change the orientation that we're drawing this from. All right, so let's go ahead and do this. And let's go ahead and, so now we're going to have a methyl on there. That's an H. That. And the perspective we're looking from is C2 to C3. So we're going to go that way. And I don't think we need the model anymore. Okay. All right, so go ahead and start it off. So we have the dot in the middle. So is my front group going straight up or straight down that we have here?
Straight down.
Yeah, this is the down situation we have here. So this one going down, and that is a methyl group. You can shorthand these further as just putting ME for short. If that helps you fit everything in there, just go ahead and do it. And then going upward here, we have some groups. And then let's just do the back carbon first. We have upward is an ME, and then HH. Now the tricky part is which direction is the methyl group on this portion going? Is it going left or right? It does matter. It does.
Oh, the wedges are right?
It's towards your right. That's not a general rule. It matters your perspective. So the way you want to think about, I think we're actually going to use the model for this one real quick. Hang on a second.
I just had a question. Is that drawing there's only 2 methyl groups or 3?
There are going to be 3, but we need to figure out where to put the third one.
Okay.
So we're basically wondering like where the heck does that one go? Is it going to go on the left or right on the front carbon? Is the situation we're at now. All right, so I'm just going to go ahead and replicate this molecule again. So here we have this, but we need to have a methyl group on there. So I'm going to go ahead and use the yellow one to represent the methyl group. That's on the wedge there, like this. Oops. Where did the carbon go? Oop. I should have brought more carbons. There we go. I have a carbon. There we go. Like that. So then the perspective is this way. So it's on the right. You see that? So essentially what I imagine doing is that you're kind of looking at the paper this way, and then that would be coming out of the page. It's to my right. That's the way I do it mentally. But once again, here's the model. This is coming towards us. From this angle, it's to the right. So very three-dimensional now. All right. So do we have a Gauge interaction in there? Yep, and we also have anti as well, right? So that's anti, this is Gauge. So I'm going to go ahead and call this the Gouge conformation because we do have one Gauge in there. So one Gauge, and then these two are anti to each other. And let's just go ahead and use that, that methyl there as our reference point. So this is the one I'm going to grab and turn. And we're just going to go ahead and go a 180, but it just repeats as you go the other half. Okay, that. So essentially here we're like that, and we are doing that. So it looks like now both methyl groups are going to be downward. Like that. And the reference methyl is here. All right. Oops, I dropped my methyl in the back. There, that methyl didn't do anything. That's on the top carbon. Let me fix my writing there. So ME back there. They made it look worse. All right, we're going to grab it again and turn it to this way. And then now this is downward, up, up. The other methyl is there. Our reference methyl is here now. We are all staggered again. Do I have a Gauge interaction here? So once again, let's go ahead and label the Gauge interactions as we come across them. So there is the Gauge. And then here we also have another Gauge. So one question I could potentially ask you guys is how many Gauge interactions are there for a full 360-degree bond rotation? All right, we're going to go ahead and rotate it again. And I am going to bring this one a full 360 degrees, just so we have enough practice. All right, methyl, methyl, H. Remember, the back carbon is not doing anything. So we're going to leave it alone. So these methyls are now overlapping. H. So we now have an eclipse conformation, and we also have it set up where the large groups are overlapping. That is a high energy conformation. Our reference one is here now. All right, again, rotate. You're going to have so much fun studying this stuff. I'm just imagining all the drawing. You're going to love it. Okay. We are now in this situation. Oop. I made a mistake there, didn't I? Nope. Actually, yeah, that's fine. So the reference one is now here, like so. And how many Gauge interactions does that one have? Yep, there's two. So there is one here, one here. So we have two Gauge interactions there. This one is higher energy than the other ones because it has more Gauge interactions than the other ones do. So this one is higher energy than the other staggered. All right. Okay, we actually have two more to do if we're going to do a full 360. Let's bring this one this way. And then I believe one more after this one would just bring us back to the start. So let's go ahead and do it down here just so we have enough room to draw it. So this methyl, the reference methyl, is now up. And also overlapping there. This other methyl is over here. And I believe everything else is the same. All right, and then doing this one more time would just bring it back to the start. All right. Are there questions about this one?
So, I'm sorry. I'm busy drawing, like listening and drawing things out.
Yep.
So for the second gouge, you skipped it 120 degrees.
Did I skip something?
Or no?
Don't think I skipped one.
Why is there an extra hydrogen?
Missing a hydrogen?
No, there's an extra one. On the back carbon? Yeah, with MEHH.
There's four.
You kind
Oh, what am I doing? Yeah, what am I doing there? You're right. I don't know. Yeah, this is supposed to be eclipse. Sorry about that. I thought it looked kind of funny. Yep, good catch. All right, so that is your other high energy eclipse conformation.
This should be an eclipse drawing, right?
Yeah, you're right. So yeah, it always goes between staggered eclipse, as you're going 60-degree increments. So oops. All right. So how many total Gauge interactions do we have to go through for a full 360? You just add them all up. So it's 4 that has to go through. And then it also has to go through this many eclipse conformations. It's what, 1, 2, 3. So if we had the energy values of all those, you would just add it all up, and then that would be the total energy required for a full bond rotation. Okay. So I definitely recommend practicing these. You're going to probably need a little bit of practice for these. You don't have time to do much more. We don't even have much time to do much more. All right, I want to go ahead and stop here. We have like, what, 10 minutes left. Wanted a little bit of a break per lab, so we're going to go ahead and stop here. Next time, we are going to go ahead and go over cycloalkanes. So let me go quickly before I turn this off here. I do want to show you the kind of things that we're going to be doing quick next week, and then we'll write it all out actually next week. So we are going to be going over the stability of ring structures. In general, it works out where the least favored conformation is actually the main way that we draw them. So for a cyclohexane, if you actually draw it flat on paper, it looks like that. But if you look at any of the bonds, what conformation is that, do you think? I'm looking at this one. That's eclipse, isn't it? So if the molecule is flat, every single carbon-carbon bond is eclipsed. Do you think nature likes that? No. So what happens instead is nature will kind of torque it a little bit, like this. So now I have it in the most stable conformation. But the thing is, though, that if you look at it now down any of the carbon bonds, they are now staggered. And the thing that we're going to have to do is we're going to be looking at whether or not groups are on the equatorial portion. So the green ones here are referred to as being equatorial because they're on the, you imagine this being a globe, they're on the equator. And then the ones that are straight up and down are the axials. And what happens here is that suppose we have a large group here, it works out where it does not like large groups here. And the reason why is because if a large group is axial, it is actually gouged to the rest of the ring. So what nature will do is it'll push it out equatorial to get it to be anti to the ring. So let me show you what happens there. So basically it's called a ring flip. So let me do a ring flip here. It's going to do this and flip around a little bit. And what changed? That's what I just did. You guys see that? What happened? So right now equatorials are white, axials are green. In a chair flip, everything kind of just flips its orientation. So now it's the opposite again. And you guys are going to have to do this on paper. I've had students tell me that they think it's actually more challenging to do with the model than it is to draw it on paper. So if you want help doing this with the model, I can help you guys, but we're going to be doing this on paper. All right, and that's basically going to be Tuesday's lecture. So if you can, read ahead a little bit. You do have acid-base to practice on. We just have more and more stuff to work on. No boredom. You guys have plenty to work on this weekend. All right.